And since I'm calling 2, 1 the initial point and the terminal point 5, 3, we draw an arrow going from, here's the starting point, and you're going in this direction to this point. And so when you draw an arrow, you're indicating a direction. So vectors, they have 2 properties that are important to identify a vector, and that is the direction and the length or the norm of the vector. So if you think of it, you could think of this angle indicating the direction and this length, we can call it, well, I don't want to call it R because we use that notation. I'll call it, well, the way we do it with vectors is if we call the vector U, we use double lines like that around it to talk about the length of the vector. So the name of this vector, let's say, is U. And the way I show that it's a vector is I put this little, it's like partial arrow above the letter. Or in a textbook, you'll see sometimes it will be in bold print. And when you see it in bold in a math textbook like that, it's indicating that it's a vector, meaning that it has length and direction. And so if I want to calculate the length of the vector, we use the distance formula. You're just calculating the distance between the initial point and the terminal point. Okay, so for our example here, we're going to use the distance formula, and we're going to take the terminal point. So we start with the x value and we subtract the x value from the initial point like this, and then square it. And then you take the terminal point, the y value, so that's 3, subtract the 1 from the y value of the initial point, square that. So this is the difference in the x, and here's the difference in the y. And it's okay if you get the wrong order because you're squaring it, and if you happen to have a negative number, a negative squared is still positive. So if you get them, unlike when you're calculating the slope, you have to be very careful to have them in the correct order. But because the distance formula, you're squaring it, you don't have to worry about it so much. As long as you take the difference of the x values and the difference of the y values. And you probably remember the distance formula for 2 points in the coordinate plane. So this becomes 3 squared, so that's 9, plus 2 squared, which is 4, so that's the square root of 13. And that is the length of your vector. All right. And typically we indicate the direction just by drawing it in the coordinate plane. And then you can see by the arrow which direction it's pointing. All right. Any questions on vectors? so far. Okay. So let me draw a picture here of two vectors in the coordinate plane, for example, 2. And we have one with initial point 2, 1 and terminal point 4, 3. And then another one, so I should probably just label these so you can see what we're talking about here. Okay. And then another vector at 2, 4 and 4, 6. Okay. And the question is, are these vectors the same? And the answer is yes. And the way we check, or the way we determine that is, as long as their directions are the same. Well, how do you compare directions of two vectors? Well, you look at their slope. If their slopes are the same, because two vectors are pieces of lines. And so as long as the slopes of those two lines that show the path or the direction of the vector, as long as the slopes are the same, we say they have the same direction. And if their lengths are the same, then they have, you've got both the same length and direction, therefore they're the same vector. Even though they're positioned in the coordinate plane at a different spot, the only defining characteristics for vectors is not the location in the coordinate plane, but the direction or the slope of the line and the length, okay? And you can just see, to calculate their slopes, so this is U, let's call it, and we'll call this one, whoops, V, U and V. And notice that the slopes the slope of U is, now order matters when you're doing slope, right? So you're going to take 4 minus 2. Those are the x values. Those go in the denominator. And then you're going to take 3 minus 1 for the numerator because those are the y values. So the slope of this vector is 1. And then we're comparing that to the slope of V. And you have 4 minus 2, that's going to go in the denominator. And 6 minus 4. So you're going to get 2 over 2 equal 1. So the directions are the same. And now we want to compare the magnitudes. Magnitude is a fancy word for length. And so the way I draw that is I use the double lines. So the magnitude of u is the square root of 4 minus 2 squared plus 3 minus 1 squared. So this becomes 2 squared plus, which is 4, plus 4, so it's the square root of 8. And if we simplify that, it's going to be 2 square root of 2, because 8 has 3 copies of 2. So you take the square root of 4 to get the 2, and then you have 1, 2 left over, and that stays under the radical. And you'll notice that if I calculate the length of v, I get 4 minus 2 squared. Those are the difference of the x values, plus the difference of the y values, 6 minus 4 squared. You're also going to get square root of 8. Since they have both the same direction and the same magnitude, we say the two vectors are in fact equal. So that's how you tell if two vectors are equal. Any questions on this one? One thing I should be careful to say, just by comparing the slopes is not enough, okay? So let me show you an example of a situation here. Okay, we have two vectors, and I'm going to draw them. Let's see here. So there's one vector, and then I'm going to draw the other one right next to it, just shift it over a little bit. Okay. These two vectors are both vertical. I mean, they're both parallel. So you would think, I mean, you can't really calculate the slope, but they're both vertical. They lie along vertical lines, and they have the same length. However, you'll notice they're pointing in the opposite direction. So these two vectors are not equal because they are pointing in opposite directions. So it's not just enough to look at the slope or to see if two lines are parallel. That will help you, but you also have to check and see that they're pointing in the same direction. So there's kind of one extra step there, if you will, when you're comparing two vectors. But they have the same length, and I should say even though. They have the same length and are parallel. Okay. So I'd like to talk for a little while about unit vectors and how those work. Unit vectors are a way of identifying a vector without necessarily giving the coordinates, because remember, vectors can float around. You can have two vectors that are positioned in different places in the coordinate plane, and yet they can be equal. So we want to have a very special way of identifying a vector without respect to the location of the vector. Okay, so the way we do that is we use what we call our unit vectors. And so let me introduce to you the idea of a unit vector. And for three-dimensional space, we have I, J, and K. And for our purposes of illustration, we're going to be working mostly with I and J. But if you because we're drawing graphs in 2 dimensions typically. But if you're talking about 3 dimensions, then you can add K to that. And so since we live in a 3-dimensional world, K is useful for that purpose. But just for purposes of examples and keeping things easy, I'll mostly talk about I and J. So in the 2-dimensional plane, we have a vector, and I'm going to position it at the origins just to kind of give you a feel for, that's kind of a standard position for vectors. When the initial point is at the origin, and it points in the x direction. So, I has length 1. That's why we call it a unit vector. And it points in the positive direction along the x-axis. And here I've written I with a dot. Typically, if you're talking about a vector, if you're just writing on paper, you're going to use this little symbol instead of the dot. So you're going to write it like that. If you're reading in a book and you see an I that's boldface, you know they're talking about the vector. They may or may not have a little arrow above it. But if you see it in bold type, then you know it's the unit vector I. And I is the same name that you use. That's just convention, okay? Now, I think some textbooks might use X with a little in boldface or with a little arrow on top to show that it's going along in the X direction. But I think I is more common. And then, so here's the I, this little vector here. And then I'll do in green the J. So your J vector has length 1 because it's a unit vector. And it points in the positive direction of the x-axis. Okay, so along with unit vectors, we have what we call is scalar multiplication. And the reason why we want to do that is because if we want to talk about a vector having length 3, let's say, and we want it to point in the x direction, we would write it as 3 times I. So that's called scalar multiplication. And scalar just means a constant versus a vector. These vectors are objects, so they have length and direction. A scalar just is a quantity, like a number 3 is a quantity. So scalar multiplication of the unit vectors. This allows us to create a vector having the same direction as a unit vector with a different length. So let's say A times I, okay? AI has length A. A is just a constant, right? So it can be kind of confusing because we use the I when we're talking about complex numbers, but it's an entirely different thing. When we're talking about complex numbers, I is an imaginary number that has the property that when you square it, you get -1. When we talk about vectors I, it's just simply a vector pointing the direction of the x-axis with length 1. So it's an entirely different thing, but they both use I. All right, let's look at some examples, and you'll see how great these unit vectors are in helping us to talk about vectors or to identify them. So so 3i, let's say if I want to draw that, I'm forgetting my little hat there, okay? So we have now, it points in the same direction, but instead of having length 1, it has length 3. So this is 3i. And we might be interested in -5j, okay? Well, the -5, the minus sign means it points in the opposite direction of j, and the 5 means instead of having length 1, it has length 5. So here is the x-axis, here's the y-axis. So if I want to plot -5j, I'm going to go down 1, 2, 3, 4, 5. So remember, j points in the positive y direction, but when we change the sign, we go in the opposite direction. So this is -5j. Now, when we add two vectors, what you do is you form a triangle. So I'm going to draw, rectangle, not triangle. So I'm going to draw a rectangle here. And so I'm going to go okay. Well, this takes me to a point out here. This is 3, -5. Okay. And then I'm going to draw, let's use purple instead. Well, I thought I had my purple marker, but I don't. So I'm going to use this one. This vector is actually 3i plus -5j, or if you will, 3i minus 5j. And every vector can be expressed as a sum of unit vectors and scalar multiples of the unit vectors. So here we have this piece gives us the x direction, and then this piece gives us the y direction. And when we add them together, we get this third vector. So the way you add vectors is you form the rectangle and then take your initial point at the same initial point of the other two vectors, and then you just add them together like that. So every vector in the coordinate plane can be expressed as a sum of the scalar multiples of unit vectors. That's a really important point. So let me write that out. And I call that a linear combination. Of the unit vectors for the sum of scalar multiples All right, so let's look at some more examples and you'll get more comfortable with this. Any questions so far? All right. This is example, what is this example here? Let me just double check here. I think it's example 5, yeah. So remember, the I vector tells you where the x, what the x coordinate is, and then the j vector tells you what the y coordinate is. So we have -2 in the x direction. So I points in the positive direction, but we're multiplying by -2. So it's going to end up pointing in the negative direction. And the length of that vector is going to be 2 units. So here's the x coordinate vector, if you will. And then we go in the +3 for y, so 1, 2, 3, and I'm pointing in the positive j direction. So the resulting vector has initial point at the origin, okay, so you just form, so this point here is -2, 3, and your initial point is at the origin, and the terminal point is -2, 3. Now this is just in standard position. You can move that vector anywhere you want. It's going to have the same length and it's going to have the same direction, and it can be expressed this way. Okay. Kind of dark in here. Let me shine my light over here so I can see for a second. Okay. Now, what is the magnitude of this vector? We'll call this new vector, we'll call it U. And we want to find the magnitude of U. So you're going to use the distance formula. And I kind of made that really long. I didn't have to do that. Because our initial point is the origin, when you subtract 0 from each of these, all you have to do is take -2 squared and then add it to 3 squared, and you're going to get the square root of 4 plus 9, which is, it's not always going to be square root of 13. It just so happens to be the same as the other one that we did. But so it's much easier to work with a vector in this format rather than if you're given an initial point and you're given a terminal point. This is kind of the standard form for all vectors, and you just take the square root of the x coordinate squared plus the y coordinate squared, just like we do for finding the length r for angles and things like that. So it's really all related, and that's why we cover all these. It's just another thing that we're working with. So you can see how useful the coordinate plane is. Not only can we use it for understanding complex numbers, but now we can also use it for vectors as well. So it has multiple uses. All right, so here's an example from your homework. This is like problem 5. And we're in section 7.6. It says, let V be the vector from the initial point P1, and it gives a point, to the terminal point. Write V in terms of I and J. So we're given 2 points, and the initial point is given to us as -9, -9. And the terminal point is given to us as 4, 5. Now, when you're calculating the length, it doesn't matter what the order is. However, you're just taking, because you're just taking the differences between the x's, squaring it, the differences between the y's. But if you want to draw the vector, you do have to take, and you want to find the I and j scalar multiples, you do have to take the terminal point and subtract the initial point. So we're going to say, okay, so we have -9, -9. I'm just going to write it like this, -9, -9. And that's that point there. And then 4, 5, so it's going to be about here. Let's say this is 4, and this is a height of 5, let's say. I've got too many -9s over here. I didn't mean to write that there. I meant to write it over here. That's better. Okay, so here's our vector. And we are told that this is our initial point. So the arrow comes right at the terminal point. And so it has a certain direction. But we don't have to worry about the direction. We just need to, we want to express it in terms of I and j. Okay, so express in terms of your unit vectors I and j. So what is the scalar multiple for the I? Well, remember now the I is the x direction. So we are going in the positive. If we start at the initial point and we move to the terminal point, we are moving in the positive x direction. And we're going to go over 9 units plus an additional 4 units. So a total of 13 units. So it's going to be 13I. And I'm just going to draw. So this is 13. And then we're going to go up from 14 units, right? So down here, we're at -9 on the y-axis, and then we go up to 5. So that's a total of 14 units in the positive y direction. Okay, so that's how you determine the this representation. And this is the standard way to think of a vector, is in terms of I and j. Oh, I don't know why I put the, I don't know why I did this. There we go. Okay. So when you're given 2 vectors, you can add them, you can subtract them, and it's really simple when it's in this format, okay? So let me show you how we do that. So we're given that U is I minus j, and V is 2I plus 5j. So if we want to take and find U plus V, okay, that is equal to, well, you just take the x scalars or the I scalars and the j scalars and add them. So here, this is understood to be 1. So if we're adding U and V, we take 1 plus 2, and that will become the new I component. And then we add to that -1 plus 5, and that will become the j component for our new vector. So we get 3I plus 4j. See how easy that is? So this is the best format to have the vectors in, and it works very nicely. I meant to write a V there. I'm having all kinds of problems today. There we go. All right, so using the vectors in example 7, we want to find 2 times U minus 3 times J. So these are scalar multiples of our other vectors, U and V. So all we do is we take 2 times I minus j, because that's what u is. And that's going to be, you just distribute your 2 to the I and to the negative j. And you get 2I minus 2j. All right. And then if you want to find 3 times v, so this is 2u, and I'm going to do, instead of 3, I'm going to do negative 3 times v. V, remember, is 2i plus 5j. So you just distribute the negative 3 through, and you get negative 6i minus 15j. And we are adding 2u, well, subtracting, we're adding 2u and negative 3v. So 2u minus 3v, we're just going to combine these, and we get minus 4i minus 17j. Okay, so it just follows very naturally all the different operations that you're doing with these vectors. And they're really simple. It's just multiplying, distributing your scalars, and then adding the I component and adding the j component values separately. It's really simple. All right, let me do number 11, similar to one from your homework. And number 11 gives you v is equal to negative 6i plus 7j. And it gives you w as negative I minus 6j. Sorry, I'm just having trouble seeing in this. Okay, there we go. W is negative I minus 9j. And we're asked to find 7v minus 8w. So you take your 7 times the v, which is negative 6i plus 7j, and then you subtract 8 times this w, which is negative I minus 9j. And so distributing our scalars, this is going to be negative 42i plus 49j. Then we have negative 8 times a negative I is going to be plus 8i, and then also a double negative again, plus 72, because negative 9 times negative 8 is 72. So this is going to be 72j. And then we combine the i's, so we're going to have negative 42 plus 8. And that is going to be negative 34i. And then the 49 plus the 72 is going to be 121j. All right. So it's not really that different than if you had variables, like x and y here. You just do the same procedure. The only difference is you're talking about vectors instead of variables. So you have your little arrow vectors when you draw them, that's all. All right, then now in the second part, no, oh, on number 12, they ask you to find the magnitude of the difference of two. So let me do an example like that. Somebody has a question here. Let me check the chat. I should be posting this lecture as soon as I get done with class here. I'll probably upload it. Okay. All right. All right, so now we're given u equals 7i minus 2j. And then we're given that w equals negative I minus 9j. And we are asked to find w minus u, but the norm, okay? When you see those double lines like that, you're finding the length. There are all kinds of words for the length of, we say the norm, that's another word for magnitude, and it's another word for length. So you've got norm, magnitude, length, and I use them interchangeably, so I'm sorry about that. But, all right. So first, we want to find the difference of u or w minus u. So we're going to do that first. And so you're going to take negative I minus 9j, that's your w, and you're going to subtract 7i minus 2j. And so since we're subtracting, we need to distribute the negative to both scalar multiples. And so we have negative I minus 9j minus 7i plus 2j. And then we combine the i's and we get negative 8i. I need to put my little hats on. I forget that. There we go. That's better. And so we've got these combined, and then we have negative 7 plus 2 is negative 5j. Okay, so here is w minus u. Now to find the magnitude of that, we are going to take the square root of negative 8 squared plus negative 5 squared. And this becomes 64, the square root of 64 plus 25, which is the square root of 89. And so that is the magnitude. So none of this is really anything new except for maybe the I and the J part, but really you're doing the same old stuff. You're using the distance formula to calculate the length, etc. And it's pretty simple. All right. Let me just check my time real quick here to make sure I don't. I think we have quite a bit of time yet. So I'm going to talk about the dot product. And this is section 7.7. So let's suppose you have two vectors. Let's suppose that u is ai plus bj, and A and B are real numbers. So are C and D. And we'll say that V is CI plus DJ. Okay. So we have these two vectors, and I'm just going to introduce this. I'm not going to finish 7.7 today, but the dot product, which is U dot V. It's a sort of like a multiplication, but it's not really, because when you multiply two real numbers, you get another real number. When you multiply two complex numbers, you get another complex number. But the dot product gives you something entirely different. You don't have a vector anymore. So here you're taking two vectors, you multiply them, and you get a number. And that's just the weird thing about dot products. So I don't really know. It does have importance in the real world, but I'm not exactly sure what. So the way we do it is, if you have U equals AI plus BJ and V is CI plus DJ, then the dot product is just simply A times C plus B times D. So the vectors go away when you do the dot product. All you do is you multiply the X coordinates, and then you multiply the Y coordinates, and there's your dot product. It's pretty easy to do, though. So for example, let's suppose you have U is equal to negative 7I plus 3J, and your V is 2I minus 8J. Okay? Your dot product, U dot V equals negative 7 times 2 plus 3 times negative 8. And so you get negative 14 plus negative 24, which is negative 38. Okay, that's all it is. Pretty easy to do. Finally, something easy, huh? Okay. And I didn't plan on reaching section 7.7, so I didn't bring my notes with me for that. So let's go take a look at the homework. And then I'll be able to refresh my memory about what I need to cover. So we're coming down to the end here. Here's section 7.7. Only 9 problems. So here we're given that V is 11I plus J and W is I plus 11J. So the dot product is going to be 11 times 1 plus 1 times 11. So it's going to be 22. So and the dot product of V with itself, well, you take the 2x, right? So it's going to be 11 times 11, or 121, plus 1 times 1, because the x's are 11, the y's are 1, so it's like 11 times 11, 1 times 1, plus 1 times 1. So it's going to be 122. Okay, so here, the dot product, you have V times W, so -8 times -10, that's 80. And then -4 times -6 is 24, so it's 104. Oh wait, can you guys see this? I'm sorry. Hold on. Nope. I hate it when that happens. Okay, try this again. All right. So here we have -8i times -10i. So you're going to have -8 times -10, that's 80. Then you have -4 times -6, that's positive 24 because you have the double negative. So you're going to have 80 plus 24, so that's the 104. Now, we're taking V dot V. So we're just focusing right here on V. The x's are -8, so I square -8 and add the square of -4 because this is V dot V, so it's like a square, right? So I take the x's, -8 squared is 64, and then -4 squared is 16. So let me think, 64 plus 16 is going to be 80. See how simple this is? It's really very simple. Okay, let's do this one on paper. I'm keeping track of the time here, so we still have 15 minutes. So let's go ahead and do this one. So example 2, I'm just going to copy this down real quick on the paper. U is 2i minus j, and notice how they're using the bold to instead of the little vector symbols, but U equals 2i minus j. All right. V equals 2i plus j. And then W equals I plus 5j. All righty. We want to find U dot V plus W. U dot V plus W. All righty. Let me stop sharing here. So first I'm going to do V plus W. And all we do is we add the x's. So we add 2, and this is understood to be 1, right? So that's going to be 2 plus 1. That'll be 3. And then we have, this is understood to be 1, right? 1 plus 5. So that's going to be 6. So you have 3i plus 6j. And now we're going to take U dot this, right? So we take 2 times 3. I'm just going to do it in the 2 times 3 plus -1 times 6. See how that works? We're just taking the scalars and multiplying. So the U dot V plus W. So the 2 times the 3, -1, I'm going to write a little 1 in here, -1 times the 6. So we have 2 times 3 is 6, minus 6 equals 0. And this is a good opportunity. There's something special about this. When your dot product is 0, that means your vectors are what we say is they're orthogonal. In other words, they're perpendicular. Hold on, another chat. Oh, yes, okay. All right. So I'll make a little note there for you. This is important because I think there's some questions in here about this. Two vectors are said to be orthogonal if their dot product is 0. Okay, this is important. That's an O, by the way. Two vectors are said to be orthogonal if their dot product is 0. So in other words, U and V plus W are orthogonal. All right, let me go back to the homework. I'll let you finish copying that first. We already did this. I'm just going to keep going to the next one. Okay, so here you're going to take 4 times U. So this is U. So 4 times U will be 4 times 5 is 20 minus, that's understood to be -1. So it's going to be minus 4J. And then you're going to take the dot product of that new vector with this W here. So, or I'm sorry, V. So it's going to be 20 times 5, which is 100, plus -4 times 1, which is -4. So it's going to be 96. 96. All right. It's now it's given, it says find the angle between V and W. And I'm going to save this for next time because that's a whole nother formula and a whole nother topic. And I've done enough today. So I'm just going to let you out 10 minutes early. And next time we'll talk about how you find the angle between two vectors. Okay. And I will post this right away when I go to my office. It'll take maybe 20 minutes to get it uploaded, but I will work on it right away so you have it. I think I did upload the recording from Thursday. You might check. I did it today, I think. I'll go check after. I will look at that also, and I'll take a look and see if that was 7.5, right? I think I did that today. So take a look. And if I didn't do it, I'll double check.